Hello students, welcome again. In this video lecture, we will start with bridge rectifier. In previous video series, what we have done is uh, full wave center diode rectifier and its analysis. Now we will start with bridge rectifier. See on screen you have circuit diagram of bridge rectifier. Hope you remember that in half wave rectifier, look at this, in half wave rectifier, we have only one diode. In case of full wave center diode rectifier, we have two diodes. And in case of bridge rectifier, now I have connected four diodes. Good. We have compared already half wave rectifier and full wave center diode rectifier. See, if we compare half wave rectifier and full wave center diode rectifier in efficiency, then also efficiency of full wave center diode rectifier is always good as compared to the efficiency of half wave rectifier. Half wave rectifier gives efficiency only 40%, whereas center diode rectifier gives efficiency of 81%. About now, even if we compare the ripple factor, then also the ripple factor of full wave center diode rectifier is less as compared to the ripple factor of half wave rectifier. In half wave, we got ripple factor of 121%, and in case of center diode rectifier, the ripple factor we got is just 48%. So the ripple factor is less, and a ripple factor has to be very less. Because what do you mean by a ripple? A ripple is amount of AC components present in the output. So amount of AC component present should be very less. That's what the desired thing. We want pure DC, and we will get pure DC only when their AC components are less. Right. So that's why a ripple factor should be as less as as possible. Right. So we had this comparison, half wave and full wave, but now we have another type of full wave rectifier, which is a bridge rectifier. That it is a full wave rectifier. It means in that rectifier also voltage is available, output voltage is available for positive half cycle of the input signal as well as negative half cycle of the input signal. So let us draw the output waveforms for this bridge rectifier. And it's not a new at all, because just check it, the waveforms that I am drawing here for bridge rectifier are completely same as that of center diode rectifier. Look at this. This is output waveform. Now you can treat this as current with respect to time, or you can call it as voltage with respect to time. Because current waveforms and voltage waveforms both are same in case of rectifiers. Now those are output waveforms for bridge rectifier, and we know that we got the same waveform in case of center tap full wave rectifier. So it means as both are full wave rectifiers, we are getting identical waveforms. As waveforms are identical, whatever analysis we have done for full wave center diode rectifier, all that analysis is applicable to the bridge rectifier. Is it? It means what I am talking about? It means if I calculate IDC for bridge rectifier, then that IDC will be equals to twice Im by pi. Isn't it same as that of IDC of center diode rectifier? Is it? If I calculate VDC, or if I derive equation for VDC for this bridge rectifier, obviously it will be same as twice Vm by pi. Isn't it same for center diode rectifier? It means whatever analysis we have done for center diode rectifier, all is applicable to the bridge rectifier. Why? Because both are a type of full wave rectifier, both are giving same output voltage. Right? So all those 13 or 14 parameters, whatever we have derived, or center tap, all we can paste here for this bridge rectifier. Right? There is a small difference. There is a small difference that I am talking about. Now I will talk about. See, all the parameters IDC, VDC, then IRMS, VRMS, then PAC, PDC, even if ripple factor. What else we are skipping? Apart from that, that efficiency, everything is same. Only two parameters are different if I compare bridge and center tap. What are those two parameters? Those two parameters. First parameter is transformer utilization factor, and second parameter is, okay, I'll write second parameter here. Second parameter is PIV, peak inverse voltage. Those two parameters are different for bridge rectifier if we compare bridge rectifier with center tap rectifier. Right? Why it is different? If we think about transformer utilization factor, then in bridge rectifier, look at this, simple one primary, one secondary type of transformer is used. But in case of center tap rectifier, there was center tap transformer. It has one primary and two secondaries. Is it? So it is one primary and two secondary. That's why we have calculated transformer utilization factor with some different manner. But here in case of bridge rectifier, we have one primary, one secondary, which is same as that of half wave rectifier. A simple one primary, one secondary transformer is used in bridge rectifier. Is it? It's not center tapping at all. So that's why transformer utilization is different in bridge rectifier as we compare with the center tap rectifier. So as if now I am telling you that transformer utilization of center tap is different from the transformer utilization of bridge, then let's calculate what is transformer utilization factor for this bridge rectifier. Okay, let's start with now. What is the basic equation we have written for transformer utilization factor? Yes, it is output power, that is DC output delivered to the load, means DC output available at the load, divided by transformer rating. Transformer ratings. Right. Now, what is that DC voltage or DC output delivered to the load? Instead of voltage, I shouldn't use the word voltage. It is actually power. Was it? I must say power. That is DC power delivered to the load divided by transformer ratings. Because if transformer ratings are there, it means current and voltage. Is it? So current and voltage, they form a power. We are calling a rating, a power rating of a transformer. So obviously, if in denominator, I'm thinking about voltage and current, in the numerator, DC output power, the word power must be there, is it? So let me correct it. DC output power available at the load. So what is the DC output power available at the load? It is obviously DC voltage VDC multiplied by DC current IDC. And what about this transformer ratings? Yes, we had discussion about that, which is VS RMS multiplied by IS RMS. Why I am using this S word? Because I just want to tell you that VS means voltage at the secondary, IS means current at the secondary. Is that? Now, put the values for VDC and IDC and VSRMS and ISRMS. Now, what is the value for VDC? It is twice of Vm divided by pi. And what is IDC? It is twice of Im divided by pi. Now, if it is a transformer ratings, then see, voltage is available for full time at the secondary. Even current is also available at the secondary for full time. It means the transformer rating I supposed to write is Vm divided by root 2 and ISRMS will be Im divided by root 2. Is it? That's what it is. Now solve it. Twice Vm, then Vm. Yes, I can cancel it. Im, and be cancelled. The only thing is pi multiplied by pi is there in denominator, and then 2, 2, 2. So it will be 8 divided by pi square. 8 divided by pi square. It means if it is 8 divided by pi square, the value will be 0.812. This is transformer utilization factor for bridge rectifier. Look at this. In case of full wave center diode rectifier, the transformer utilization is 0.69. Is it? Even if it is a center diode rectifier. But here it's a bridge rectifier. The simple one, primary one, secondary transformer I am using. Then also I am using the transformer is about 81%. Look at this. It's around 81% transformer has been utilized. Is it? So now as a transformer utilization factor, this thing is done, and that is the only difference between the center diode rectifier and bridge rectifier. Is it? Now the second parameter which is different from the center diode rectifier is PIV. It means it is peak inverse voltage. Is it? It is a diode rating basically. Diode rating means the maximum reverse voltage that can be applied to the diode without getting damage. That's what peak inverse voltage. Peak means maximum, inverse means reverse. So maximum reverse voltage that diode is handling in that case. Look at this. Now what we have to find? We have to find the diode which is in reverse bias. Is it? The diode which is in reverse bias, and in reverse bias how much maximum voltage that diode is handling. Is it? Now if if I start with the operation, then look at this. During positive half cycle, just check out the operation, you will understand what is PIV. Now, during positive half cycle, what will happen? This diode, okay, let me call it as diode 1, diode 2 and diode 3 and diode 4. 4 diodes are there. During positive half cycle, diode D1 will start conducting. Why? Because the anode is positive. Is it? And here this is positive. And look at this. This phase is negative. Is it? So as anode becomes positive, and here the cathode of fourth diode becomes negative. It means it has to go into the forward bias, and this has to go into forward bias. It means 1 and 4, diode number 1 and diode number 4 will start conducting. So now current will start flowing in this direction. Look at this. This is what that current flows. The complete cycle is there. Now in that case, diode 1 and 4 is in reverse bias, is in forward bias. Then 2 and 3 are in reverse bias. Is it? As 2 and 3 are in reverse bias, take any one diode and calculate how much reverse voltage they are holding. Now look at this. If I consider diode 2, then this voltage is positive and diode D1 is conducting. It means, let me make it short circuit. So this positive voltage is here, just assume, and this negative voltage is there. Is it? The only one peak is handled by the diode, as if this diode 2 is handling only one peak. One peak means I am talking about this voltage. Look at the waveform. I am talking about this. So in bridge rectifier, the diode which is in reverse bias handles only one peak, and it means it is the maximum reverse voltage that is handled by the diode. So it means peak inverse voltage will be Vm. Is it? In case of center diode rectifier, what was the peak inverse voltage? It was twice of Vm. Is it? Because one diode is in forward bias, another diode is in reverse bias. Is it? If this diode is in reverse bias, then this diode will handle the voltage from the upper arm and even the voltage from its lower arm. So upper arm Vm, lower arm Vm. Total twice Vm voltage has to be handled by this diode which is in reverse bias. So in center diode rectifier it was twice Vm, but in case of bridge rectifier, the diode which is in reverse bias is handling just only one peak, that is Vm. So its peak inverse voltage is Vm. Right. So those are the only parameters which are quite different. Otherwise, the rest of the parameter are completely identical with the center diode rectifier. Is it? Now, this bridge rectifier, if we check this circuit diagram, if we observe the circuit diagram, those four diodes are forming a balanced bridge. Is it? We can't say balanced as it, but they form a bridge. Is it? They look like first arm, second arm, third arm, fourth arm. Four arms are there. Is it? Four arms are connected. Look at this. One anode and one cathode. The combination of a cathode anode is there. Again, combination of cathode anode is there. Two cathodes are connected. Two anodes are connected. Isn't it a nice bridge? So that's why just by observing the structure, is it, the infra of that circuit diagram, it is called bridge rectifier. That's what. Otherwise, there is no technical reason as such to call this circuit as a bridge rectifier. It just forms a bridge of four diodes. One diode will handle one arm. So that's why it is a bridge rectifier. Is that? Now, up to now we have seen analysis of three rectifiers: half wave, full wave, and even bridge. Is that? So the circuit diagram, its operation and analysis part is done. Now, in probably in next lecture, what we will do? We will start with filter theory. We will start with filter. We will discuss that if at the output I am getting pulsating DC, then look at this. This is what pulsating DC. And if this is pulsating DC, how this pulsating DC has to be converted into pure DC. That part will be your filter. So from next lecture, we will start with filter. Is it? Thank you very much.